7-8 years ago, I was not aware carbon fiber plays such a big role in the infrastructure industry. If you had been attending yesterday's StratView sessions, uh, even they have a significant uh, pie contribution of infrastructure, which takes a lot of composites into it. And recently, even in India, there is a good acceptance of carbon fiber for resilient infrastructure in this particular sector. And today we shall have a look at how. Just a normal disclaimer, the analysis and the sharings over here are just for this audience and for today's discussion purpose. And these are something which I have created. Let's all not hold the company against what views I present over here. What I intend to give you as takeaways today are how carbon fiber helps you to enhance strength of the infrastructure, extend these assets' life, obviously lower the cost, and give a quick turnaround of the project. Well, where did this come from? Any answers? Come on, all of us have seen broken bones. So what is the solution for a broken or a broken leg or a fractured leg? Sorry? Bang on. You have some plates or rods inserted. You need to hold them together. So you need some bolting mechanism with your bones. And what you do? Come on, guys, this is not the end. Wrap it or plaster it. All on the same page? You need a plaster, you need to strengthen it with some plate, and you possibly need to immobilize the failure zone. Bear this in mind when we come back to it. Let's have a look at some of these common images you would have seen everywhere except this university. The building is quite clean. So what comes to mind when you see such kind of degraded assets? You have corroded, leaking pipelines. You have columns which have rebar coming out. You have cracked columns. You have corroded jetties at ports. Is it really the end of life of these structures? So why is Reliance presenting this? Let me give you a background before we come back to the topic. Reliance has this 200-acre campus, and some of you who were yesterday attended my as well as one of my colleagues' presentation. We have this integrated campus which has an array of all the composites manufacturing technologies under one roof. In-house, we have both the resin and the fabric weaving plants, pultrusion lines for both carbon and glass, filament winding for specialized applications, wind blade for obviously the wind sector, mass transport for complicated, complex shapes. Not only that, we have in-house dedicated application development center to tune these solutions for the market. The design teams and the product development teams look at art to part or a concept to consignment, build to print, or a full service provider aspects. We understand we single-handedly cannot do everything. So for reasons beyond our capabilities, we definitely reach out to universities, IITs, subject matter experts, consultants, vendors, suppliers. even quality third-party enable accredited quality labs. And in-house, we leverage our best practices available to deliver the product development or the solution. So we have our compliance to business ethics. We have policies around health safety. Uh, the product to be delivered is also handled by our ERP, IT, supply chain, and many other support functions. In addition, yesterday you would have seen Dr. Alpa, who talked about learning and development. We also had a panel discussion around it. So those programs are continually uh, reskilling or bringing up the skill set for our talent pool, as well as being able to cater to good quality products. So today we are looking at the sector served, which is focusing on the construction, infrastructure, retrofitting, rehabilitation, strengthening aspects. And the spectrum of applications that we deliver: bridges, buildings, chimneys, silos, storage tanks, pipelines, building slabs, retaining wall, towers. The list is endless. This is just a glimpse for you. And believe me, in my 8 years at Reliance, we have catered to each and every one of these products using carbon fiber. I'll not spend time on this. We have, for last 2 days, you have seen most of these examples of why FRP is the better choice in some certain aspects. Of course, it's not a one-fit-all solution, but these are some of the glimpses of advantages that FRP offers. At Reliance, we have two brands catering to it. We have a Relex brand, which caters to the glass fiber composite solutions, and we have a Relinforce brand, which caters to the carbon fiber solutions. Typically, carbon fiber benefits with high strength up to 3 GPa plus, low weight. We talked about a fifth of the weight of the steel. Thermal compatibility, fatigue behavior, and of course, it's a material which can be tuned well with process combinations for an optimized new product development. We convert fiber to both fabric form and laminate form. Various combinations of it are available in terms of unidirectional, bidirectional, various GSMs, a very big spectrum ranging from 90 to 100 and 1200 GSM. Excuse me. Pultrusion laminate forms of these are available from 1.2 mm right up to 5 mm thick. We have two different resin systems that we provide solutions in, both epoxy and PU. And the support systems of glass fiber, the resin system, surface preparation are all available along with the solutions that we offer. Let's come back to something we saw. I still didn't get an answer whether, do you think it's an end of life? We just scrap the asset, build a new one? So why are we talking about that? Every asset has, on the X scale, you have a life, which is percentage, 100% life. Operational performance, 0 to 100. Any asset is, or any product is loaded at the start of its life. You don't immediately load it 100%. There's a small increment that is done. It's ramped up, maybe around 80-90% of its peak operating capability. Somewhere during the internal phase, it is heavily loaded. 100% operational efficiency is demanded to extract the best of the asset. After which it starts degrading. It doesn't give you that same kind of performance that is intended for. That's where it starts dipping, and probably it would collapse at its end of its life. If you can infuse some rehabilitation, some strengthening before it collapses completely, you can have an option to both increase the life as well as possibly increase or maintain its operational efficiency. It may be 100%, it could be higher than 100%. depending on the kind of reinforcement you can give, depending on the core structure itself. So at Force and at Reliance, we transition these degraded assets, the corroded pipelines, the columns, slabs, jetty piers, using standard procedures, codes, guidelines, which help calculate the kind of contribution a reinforcing mechanism can give to an existing structure, defining the problem statement, incorporating those calculations into the problem statement, finding a solution, not just relying on our calculations, we go outside, vet it with certified structural engineers, consultants into this. So yes, all these 4 cases can be brought back to life. Its life can be enhanced. Its operating performance can be maintained or enhanced. How? Let's take a glimpse into it by a couple of case studies. But before that, I'll just like to take you through what all types of rehabilitation or retrofitting can happen in case of civil infrastructure. So you have a flexure strengthening of beams, slabs, columns, shear strengthening mechanisms, seismic retrofitting. Seismic is related to earthquakes, cracks, surface preparation. Dr. Uchel talked about the surface behaviors a few minutes ago. You have tall structures which are susceptible to both stiffening as well as the seismic effects. Bridge structures which are subjected to live vehicular motion and loads. Pipes and tanks. All these are cases where the incumbent or the conventional structure might be of metal or concrete. And after certain use of its life, it calls for help. It cannot take on anymore. And that's where carbon fiber can help it to withstand more. Let's look at how. So I'll be taking you to a couple of case studies. Chimney strengthening in a high-rise building. What is the situation in this particular case? It's a case of a 100-meter tall industrial chimney. It has cracks in it. It is leaking. Of course, it's not good for the industry around it. The task is to arrest this leakage and structurally strengthen it. The way we approached it, we had 2 particular guidelines that we used. Solving the leakage by designing it with ASME PCC2. It is a guideline for pipeline leakage. And for the strengthening purpose, we used a combination of finite element analysis to identify the load paths, the stresses induced, and using ACI 442R, which is American Concrete Institute's code for strengthening of civil structures using GFRP or CFRP. If you look at the figure on the top left, it is the views of those chimney where there is an intersecting pipe creating a junction. That has actually created a weak zone because under wind loads at this particular tall structures, there is a deflection in the chimney. That deflection combined with its inherent degradation of the wall thickness led to propagation of a crack at the bottom left. Now, if you see the stresses, they are exceeding 450 MPa already in steel, which is already gone. And cracks don't stop. They continue to expand. So at the tip of the crack, we identified what are the stress locations, what is the failure modes, and how we can arrest them by creating a carbon fiber junction or a bandage or a plaster around it. That plaster not only reduce the stresses from extremely high failure modes to under the safe working limits of the steel which was there, but it also reduced the peak displacements of the chimney under the high wind loads. The solution that came out was a combination of CFRP fabric and laminate with the resin system and the top coats compatible with the surrounding corrosion environment. Because industries typically deal with corrosive effluents or chemicals. You need some system which can withstand that. At the same time, be ready for the environment and the UV protection. Coming to the second case of a high-rise building, the situation here was more from a preventive maintenance perspective. This particular tall building was in North India, where recent seismic activities have created an awareness in the builders that their original designs need to be protected for a higher seismic zone activity. And some of them are taking precautions by strengthening their own structures for higher loads. Now, a simple way to do it would be to increase the concrete jacketing around it. But in any building, or be it residential or be it commercial, floor space is at premium. You can't just increase 20, 30 mm of column jacketing and lose out on your floor space. If you're looking at a parking lot, if you're increasing 100, 200 mm thickness on a column, you're eating into the parking lot of the vehicles and you can't park your vehicle. Now, how do you overcome that? Carbon fiber, with its strength, tensile strength, 10x of steel, with its modulus almost equivalent to steel, density 1/5, eliminates all these problems, not only by providing the strength, but almost a 1/10 of its thickness of comparable steel, and at a weight penalty which is negligible. So there is no dead weight penalty on the tall structure. Here, the solution was to increase the higher load bearing capacity of the columns. So these were handled by ACI 440 again, 2R, in a confinement of the column. So here the procedure was to look at solving each and every column of a building, because as you increase the floors, the loadings of the columns change. So it's not a one fit solution for the entire building. Floor by floor, column by column, each of them have different requirements. A typical building would call for maybe about 100, 200 columns which are under severe stress. I'm not even talking about all the columns in the building. When you're talking about a particular calculation for solving one column, it has 57 parameters in it to calculate and solve for making the case acceptable. You multiply that, it's tens of thousands of calculations for one building. Automation has to be in place. It's impossible to do it manually. At the same time, you have to optimize it. You cannot give a solution which would be one fit all. So you have to identify grade optimization. You have to identify what is the problem solving, what kind of axial load compression that you're enhancing, whether it is calling for shear, bending moments, everything that students have been doing in their individual calculations for mechanics of structures, scent of materials, so on and so forth. Here we look at geometry, material properties, their strain limits, load capacities, type of solution to be provided. And we don't stop there. We also have to look at on-site installation feasibility. That means if a solution is giving you carbon fiber, which would take about 8, 10, 15, 20 wraps, is it practically possible to implement that on the site? It's very difficult. To do that many wraps, cure each and every wrap, and apply the next layer. That's where we have to also look at wrap scenarios where the number of wraps to be done on site need to be calculated. At Reliance, we have prepared our in-house calculator to automate this part as well as be able to optimize the part. The result is enhanced load-bearing capacity of the column. Typically, these are the numbers that come out, about 30 to 40%, because they are again limited by the core strength of the column, which is the concrete. The concrete gives up, there's nothing a bandage can do on top of it. If your leg is broken altogether, our bones are already broken into multiple pieces, there's nothing a bandage or a plaster can hold. So it's all dependent on the concrete strain. And the solution works as a wrap around an existing system. So it goes hand in glove with the existing system. And here we have optimized the layer count for minimizing the solution from a labor perspective as a project turnaround perspective. So not just the strengthening perspective, but to meet, match, and overcome the competitors, which are steel and concrete. These are the kind of efforts that you need to take beyond a technically feasible solution. All in all, in summary, my 3 takeaways for you: enhanced strength, extended asset life, quicker installation, all feasible. Use cases: revitalizing old assets, conversion of existing buildings into data centers. AI is gobbling data like anything. We have seen many cases where existing buildings which were not designed for higher loads now being converted into data centers with 1.5, 2x loads. Builders get increased FSI for original buildings. They want to raise a floor or two. Increased vehicle movements on flyovers. Again, live loads are increasing. How do you take care of that? You can't just increase your column pillar on the floor because it's already in the middle of 2 traveling lanes of traffic. Extended asset life, typically 10 to 20 per years lifespan is something that we have seen possible in the infrastructure industry. And reduced overall project costs in terms of total cost of ownership, because it's a faster turnaround, faster installation. You're looking at 24, 48 hours of installation and the load is already started taking up. Concrete takes cure time of 3 weeks. You're talking about 500 hours for installing it, and then it will start taking up loads. Here you're doing it over a weekend and the next Monday it starts taking load. No hard work, so it's safer, especially in chemical or petroleum assets. And all in all, that is something I hope you will find useful if you want to explore a new dimension of use case of composites in the infrastructure industry, especially with carbon fiber. Thank you for your time. Thank you.
Thank you, Rahul, for a very interesting subject where retrofitting of infrastructure can be efficiently been done by composites using various fiber strength and composite. I would request Chauhan sir to please felicitate.